All right, so we've learned many different techniques this semester for different iterative methods to solve these systems of equations. And so a great question to ask, which was asked a couple of times in the discussion forums and other times as well, is how do I know which method to use? So first of all, let's just look at some of the methods that we have talked about so far. So when we first started off with this class, we learned about Jacobi, and then we learned about Gauss-Seidel. So Gauss-Seidel was sort of a modification of Jacobi. If you remember, we were updating each entry in the vector in each iteration instead of waiting to update the vector. And then we looked at successive over-relaxation, and this was sort of a modification of the Gauss-Seidel, where we had this relaxation parameter that we were taking sort of more than a unit size step in the right direction. We were taking a bigger step in the right direction. But then an important thing is that we actually saw that these are all really just preconditioned These were all just preconditioned Richardson iterations. And in one of the most recent documents that I posted, I sort of derived Richardson iteration. I give one derivation for Richardson iteration in the case of dealing with matrices, that is. And then that's really going to be how we view these three methods right here. Not as methods in their own right that we're going to sort of implement by themselves, but as preconditioners for some other methods. So what other methods did we learn about, and how do we know which method to pick? Well, I'm going to list out some of the methods that we have learned. And some of the methods require that the matrix satisfy certain properties, and some of the methods don't require that the matrix satisfy certain properties. So we're going to go through some of these right now. So the most general, the method that is kind of the most general that works for any type of metric, any type of matrix, is GMRES. This any matrix. So any matrix is going to work here. And I'm going to come back to talk about more methods that work for any matrix, but this is one of the big methods that we looked at that works just for any matrix. Now, there are similar methods that we looked at as well, like full orthogonalization method and the various indirect orthogonalization methods also work. For all matrices. Okay, but the main way that we sort of looked at FOM was when we then looked at symmetric matrices. Okay, so what are some of the methods that we looked at for symmetric matrices? Well, we started off by realizing that in the Arnoldi algorithm, if we had a symmetric matrix, well, think about what happens. The Hessenberg matrix is going to be tridiagonal, because if your matrix is symmetric and you've got VM, HM, VM is equal to A, this means that HM has to be symmetric as well. We discussed this in some of the previous videos. Well, if the Hessenberg matrix is symmetric, that means it has to be tridiagonal. And so we get this shorter recurrence. That's one way to sort of derive why we have a shorter recurrence, simply because all of the vectors are already orthogonal. The entries in the Hessenberg matrix H, or in the case of a symmetric matrix, we call this T, for tridiagonal, those represent the, in exact arithmetic, the entries of that matrix represent the dot products or the inner products of the vectors. And so if you have a tridiagonal matrix, if you pick a vector, go to its column, the entries in that column represent the dot product of that matrix with all of the other indexed vectors in that column. So if you have a column J going entries 1 through n, the first entry in column J is going to be the dot product of the jth vector with the first vector. The second entry in the jth column is going to be the dot product of the jth vector with the second vector. In general, if you look at the ith row in the jth column, that's going to represent the inner product of the jth vector with the ith vector. Okay, so if you have this situation where only 3 entries can be non-zero, what this means is that each vector is orthogonal to almost every other vector except for the vector with the index before it and the vector with the index after it. So we get a much shorter recurrence. And so this is when we can do something like D-Landschaus. Landschaus or direct Landschaus. So if we have a symmetric matrix, then we can do D-Landschaus. And then what we saw is if we have a symmetric positive definite matrix. So not only is it symmetric, but it's positive definite, meaning all of the eigenvalues are strictly greater than 0. In a case like this, we saw that we could do conjugate gradient. And this was sort of derived from D-Landschaus, or some of the principles in D-Landschaus. And after we got D-Landschaus, we realized that if, in addition, the matrix was symmetric, positive, definite, there are some observations that we could make, and we don't have to go through the whole process with D-Landschaus, which, if you remember, we went from Arnoldi to Landschaus, and Landschaus, if the matrix is symmetric, like I just mentioned, you get these shorter recurrences. You can do kind of a direct Landschaus where you're constantly updating the vectors. You can look at some of the videos that I did then. And from that, from the output of the algorithm for D-Landschaus, we were able to sort of rederive this conjugate gradient algorithm, or derive the conjugate gradient algorithm. So it's sort of like we got to the same place going different ways. Maybe the conjugate gradient algorithm was a little bit, the derivation of the conjugate gradient algorithm was a little bit more direct, but we sort of needed to do this part first to see that that was there, so to speak. So if your matrix is symmetric, positive, definite, conjugate gradient algorithm is a great algorithm to do. Okay, another algorithm that we can look at is the biconjugate gradient. The biconjugate gradient, also, this is going to work for any matrix. Biconjugate gradient algorithm is going to work for any matrix, and it's sort of a modification of this matrix here. I sort of have this backwards, right? So the biconjugate gradient is a modification of the conjugate gradient to a case where the matrix is not symmetric. So it'll work for any matrix. And then from there we looked at a couple of others. We looked at conjugate gradient squared, and then the biconjugate gradient stabilized. So the way that we did this is we saw that conjugate gradient squared is a modification of the biconjugate gradient, and then we saw how we could take sort of a polynomial interpretation that we got from the conjugate gradient squared, and then apply and then modify that to get the biconjugate gradient stabilized. So if we want to do in the kind of FOM family for a general matrix, this is going to be the one that we use. So if we have just a general matrix, we could use either GMRes or BigStab. Now, they both will produce solutions. They're both producing solutions to a system of equations, and they can both be done on any matrix, okay? But BigStab sometimes can have, it can break down in ways that GMRes can't. So one of the reasons people like GMRes is because the residuals in each step go down. That's not exactly true for these methods here, but the stabilization in BigStab is exactly to deal with that, to sort of, if you look at biconjugate gradient or conjugate gradient squared, one of the issues that I mentioned in one of the documents that I wrote is that what's happening for conjugate gradient squared, for example, what's going on is that we are squaring both the good parts and the bad parts of the matrix. So this conjugate gradient squared could sort of make the residuals oscillate. Maybe like overall go down, but kind of oscillate a little bit. Whereas Bixtab, the stabilization part is to get rid of those oscillations. So again, GMRes is like a great workhorse. It's gonna work. It minimizes residuals. So we like this. Works for any matrix, but Bixtab here also works for any matrix. Conjugate gradient, you need to have the matrix be symmetric, parse definite. Wow, symmetric and positive definite. So if you're in the case where you have a symmetric positive definite matrix, conjugate gradient is probably going to be one of the things that you want to use. Now, we can look at GMRes and we can sort of say, okay, what if I want to do a GMRes type of algorithm, but I know where the matrix is symmetric? So in this case, if I know the matrix is symmetric, then I can do something called MinRes. This is not, I mentioned this a little bit in one of the recent documents that I uploaded, but MinRes is essentially to GMRES. MinRes is to GMRes sort of what Lanczos is to FOM. And so you can hit sort of a dminres and this sort of thing. But another way that you can implement MinRes is with the conjugate residual algorithm. So the conjugate residual algorithm, and that I gave sort of a detailed derivation in one of the documents. So conjugate residual algorithm is also a good algorithm to use, and it only requires that the matrix be symmetric. Okay, it doesn't need to be positive definite, but it does need to be symmetric. And a lot of the matrices that we come up with for the PDE stuff are going to be symmetric. Now, mathematically, in exact arithmetic, the conjugate residual is exactly the same as MinRes, and if the matrix is symmetric, they're both the same as GMRes. Okay, so that's an exact arithmetic. Now, the same things that I mentioned happening over here can happen with the conjugate residual algorithm. You can have breakdown in places where MinRes and GMRes would not break down. So MinRes is in some sense a little bit more robust. Now, from conjugate residual, you can kind of go through all of these other phases as well. You can get a biconjugate residual, you can get a conjugate residual squared, and then a stabilized version of conjugate residual as well. But we didn't talk about those at all, except for right now. And these things right here I have only discussed in the documents that I wrote. Okay, so this is sort of an overview. So if you want to sort of do a decision tree, if you kind of want to do a decision tree, then we can have something like the following. If A is any matrix, the main methods that we have seen for solving such an equation are going to be GMRes, and Bixtab. That's kind of like for any matrix. So if you don't know anything about your matrix other than it's a matrix, you can use GMRes or Bixtab. Now, if A is symmetric, some more things start opening up. We could use actually. So let me come back up here. We also saw that for this case, for any matrix, we also saw that the incomplete orthogonalization method was also working, and then we also had FOM, the full orthogonalization method. Now, these two methods are typically not going to be the ones that get implemented. For example, like SciPy and other libraries do not have these implemented, but it does have these two implemented. But these are two things that we could use. But I guess what I want to point out is the main things that we used, the main things that exist and are used are GMRes, and BigStab. But FOM and IOMK also work. Okay, now if A is symmetric, well, of course, we could use any of the methods up there, but there's also other methods that we could use. So we could use, well, the primary ones, the primary methods that are going to exist for a symmetric matrix. If we just know it's symmetric, but not necessarily positive definite, something like minres or conjugate residual are going to be the ones that get used. And there's other residual methods that also get used as well that we haven't talked so much about. But another thing that we could use would be something like a direct Landschau's method as well. But again, these two things that I listed first are kind of going to be the main ones. Okay, and then finally, if we know that, hold on one second. Going along up here, some other things that we could also use would be like biconjugate gradient. We could use like biconjugate gradient up there as well. Okay, and then we could also use conjugate gradient squared. But again, the main thing is going to be BigStab. So the ones that I have circled are kind of the ones that are most popular, that is implemented by SciPy or DEAL2, which is the differential equations library. Okay, then finally, if A is symmetric and positive definite, okay, the one that we really are going to want to use is going to be the conjugate gradient algorithm. That's going to be the number one that we want to use here. Okay, and then of course we could use the symmetric algorithms or these algorithms as well. And then with all of this we can do preconditioning. So we could take these and we can and often should somehow precondition. Now, an important thing to keep in mind is for these methods up here, any preconditioner. Any preconditioner is going to work. But down here, if we look at the preconditioners that we have to use in the case where the matrix is sparse and positive definite, then we can only use an SPD precondition. We can only use a sparse positive definite, symmetric positive definite preconditioner. So for example, up here we could use the Gauss-Seidel or an SOR preconditioner. We cannot use a Gauss-Seidel or SOR preconditioner down here because those are not going to be symmetric or positive definite. So really, it's the main one that we're going to use down here, like for conjugate gradient. This is what you're doing in the project. Would just be the diagonal matrix. That would be a good a matrix that we could use that is symmetric and positive definite. Other things would be like tridiagonal things and stuff like that. Anyways, so this gives this ending part right here, I hope answers some of the questions about, given my matrix, which method am I going to use? As you can see, GMRes and BigStab are kind of the big workhorses, and then conjugate gradient is going to be used when your matrix is symmetric and positive definite.